The HRV is heat recovery and ERV is energy recovery. And the simple difference is that heat recovery recovers heat, like it already says, and energy recovers not only heat, as well the moisture. Hello and welcome everybody to our next coffee talk. And this time we speak about HRV and ERV. So really geeky stuff. So Julia, we already talked about it last week a little bit, what HRV and ERV is. Do you want to say something about that?
Yeah, I think last time we focused a little bit more on the air tightness versus the ventilation and why both of them are important. Today we want to go a little bit deeper into the technical truths and the technical terms of HRV versus ERV.
The HRV is heat recovery and ERV is energy recovery. And the simple difference is that heat recovery recovers heat, like it already says, and energy recovers not only heat, as well the moisture. Yeah, so that's the difference. And that's what I want to have really early on in our talk, so that if you have not heard of it, at least you heard it now and you know what you're talking about. It's the energy recovery we're speaking about, or the heat recovery. So you're speaking about how much we can recover of the energy flows or the air flows between inside and outside that stays in the building. We actually haven't even spoke about percentages. We can recover up to 96% on an HRV. So when we're only recovering the heat, and an ERV, it's a little bit lower, but we are recovering the moisture as well. I think it's nearly 90%, 80, 87, 18, something like that. I think that's where we are now from a best perspective. But yeah, that's where we are with HRV and ERV. And last week we already went into technical, but this one is really geeky. So let's jump in.
All right, great. So I think the question is now that Daniel explained what the difference is between the two, or what it means, is why when would we use the one versus the other? For that, we maybe want to recap a little bit from last week for why we ventilate and why that matters. So maybe we should go into that first, and after that we can decide which of the two systems we use for our project.
Okay, so let's break that down again, just to make sure that we're all on the same page. We
Exactly.
build a building airtight to protect the building envelope and make sure that the occupants are not getting dirty air through the buildup that comes in with mold spores and pesticides and whatever has been used of treating the materials in there, fiberglass, whatever. We don't want that in the occupant space. That's the reason we put that air tightness layer in. So that's our air tightness. And then we make holes into the air tightness, what sounds a bit counterproductive, but this is now designed ventilation, these holes, that we're actually allowing air coming in. Then we went further. Ventilation is something we need consistent. We need it all the time, but our naturally occurring forces, so in other words, wind and pressure differences, they're not occurring all the time. That's the reason at the end we need a mechanical force that guarantees us a ventilation option between inside and outside for 24/7 at every climate, every condition. But then we spoke about, if it's super cold outside, we don't necessarily want to open our windows. And when it's super hot outside, we don't want to open our windows, but we still want to ventilate. Yeah, so now we're coming to the heat recovery ventilation unit that actually separates the indoor environment from the outer environment from a thermal perspective. So that's a HRV, and the ERV separates the indoor environment from the outer environment from a heat perspective, but as well from a moisture perspective. So the internal moisture stays internal, the external moisture stays external. Yeah, so that's what we're doing with this heat recovery ventilation unit. In other words, it helps us to separate these two environments from the inside and the outside. And sometimes the one makes sense and sometimes the other makes sense. Okay, I think we explained that already a bit. Or do you want to say something additional to this, Julia?
No, I think that's a really good explanation. So it explains what the difference between the two are. I think we should mention that there is another option within the two systems that's called a bypass. So maybe we want to explain what that does, because yeah, it's important to have that as well.
Yeah, so let's break that down. So say the external condition is in favor of the indoor condition. So in other words, the temperature is good and the moisture is good outside. both of these conditions are better outside than inside, then we want to bypass the recovery because we don't want to separate the indoor and outer environment in this case. We actually want to get the outer environment in. We have this so often in normal houses here in Australia that the outdoor condition is far better than the indoor condition.
That's right.
Because like you, Julia, your house is a perfect example for that.
Yes.
I would say. Do you want to explain what you have to do to actually get your temperatures up in the springtime or something like that?
Yeah, it's crazy. The house actually cools down at night a lot, and then the outside, you go outside and you think, oh, it's actually a nice warm day, while inside you're actually still cold in the morning. So we're trying to open the doors and let the warm air come in because now the outdoor is in favor of the indoor. So it's actually nicer outside, and that's a really good example. Also in summer, the other way around, where it heats up inside, and then you want the where I live, it's called the Fremantle Doctor. So it's the wind that's coming in the evening. So you want that condition inside. You don't want to recover what's already happening inside. You want that straight temperature, and the moisture is usually pretty good here in Perth as well. It's pretty dry in summer, and you can have that straight inside. You don't need to recover anything. And that's similar to what a bypass is doing. Obviously, I'm not getting it through a mechanical ventilation system. I'm getting it straight through my windows, because I don't unfortunately have a mechanical ventilation system, which I think would help a lot.
Yeah, so in other words, you're not living in a passive house, you're living in a
No.
conventional single-story Australian home that has
Yes.
exactly all these problems that we know,
Mhm.
and that's the reason it's easy to be excited about passive house because we can do it far better. And that bypass situation that is so much more happening in these conventional homes, like Julia just described it, is as well happening in a passive house, but in far, far less situations. But we still want to use that benefit if you have that benefit, if
Yes.
the outdoor is better than the indoors. Yeah. That's the reason we're having a bypass. Most of the times, especially in Europe, they call it summer bypass because they only do it in summer. But I must say, this is only a programming issue. We want to have a bypass as well in winter, a winter bypass. So when the outdoor condition is already outside 22 degrees, inside is 18 degrees. So let's get this 22 degrees in. We don't need to go through the heat recovery ventilation unit. So
Exactly.
that's the bypass. So outdoor condition is better than indoors, bypass. Now we come to the situation where the outdoor temperature is not in favor of the indoor temperature, but the outdoor moisture is in favor of the indoor moisture. So we're having the situation that we're breathing and sweating and cooking, showering inside the building, and that creates moisture buildup in the house. And normally we want to move that moisture out again. Yeah. So in a normal situation, we have the situation outside. We have a temperature that is too low or too high, but the moisture outside, the moisture absolute content would be in favor of the inside because it reduces the moisture content in the home. So that's in a mild climate. Yeah. So when you have, say, above 15 degrees and below 30 degrees, if it hasn't been raining, then we're exactly in that situation. Yeah. That a heat recovery ventilation unit is now exactly perfect. It gets rid of the moisture and it keeps the indoor temperature indoors and the outdoor temperature outdoors. That's now the HRV. Now we're coming to the more extreme situation where the outdoor moisture content and the outdoor temperature is not in favor of the indoor condition. Yeah, so that means we have outdoor, say, too hot and too much humid, so hot and humid climates. There, it totally makes sense to put an ERV in there because it separates the indoor environment from the outdoor environment from a moisture perspective and from a heat perspective. So the indoor moisture stays indoor, the outdoor moisture stays outdoor, the indoor temperature stays indoor, the outdoor temperature stays outdoor. And this really makes it possible to save so much energy. In these circumstances, we often have the situation that we then need a little bit of dehumidification in the house. Because if we're having this ERV exchanger and we're creating moisture inside and it's more than we're getting rid of, then we need to get that moisture off with a dehumidification unit. But that the PHBP will tell you, like the calculation in the Passivhaus planning package will give you a feedback if you need it or not. Okay, now that's hot climate. Everybody knows that. But The same situation would be in the cold climate, the extremely cold climate. Traditionally, passive houses were getting too dry in winter because they didn't have an ERV unit. Yeah, so your floorboards start cracking. You started to get itchy skin and a sore throat because the air was too dry. And that's the reason everybody said you need to have your air drying happening inside the home so that the moisture of your clothing is staying in the house to actually get that humidity in. Yeah, so when we're using a HRV system. Now we understand, soon we use an ERV system in an extremely cold climate, then we can actually have the same benefits. So in other words, inside we're creating too much moisture, but outside is even less moisture because the temperature is so low. Low temperature means we cannot hold so much moisture. That's the reason we want to keep that moisture inside. And because of the exchange that they're having anyway, by opening doors and windows, normally the moisture content stays in an acceptable level. Yeah, instead of dry air, we're having acceptable moisture in the air in a cold, extremely cold climate. Yeah. Just from memories, what is just coming to me, maybe you remember back in the days, if you're coming from Europe, in front of your radiator, you had this little bucket hanging with a fleece in it and water. You remember, Julia?
Yeah, I remember. That was for humidifying the air.
That was for humidifying the air back
Yeah.
in the day when we had a lot of radiators running and making the room warm. And then you need to refill that on a daily basis or like once a week, depends how big the container was and what's the condition. But yeah, this is what we try to avoid with that by keeping the moisture in and keeping the moisture inside, the heat inside, and the moisture outside, and the heat and the temperature outside. So we're separating the climate from a thermal perspective and from a moisture perspective. So extreme weather conditions, climate conditions, ERV, mild climate conditions, ARV. Cool. Is there anything else we should say here?
Yeah, so I think this is a really good explanation, extreme climates, but how would I know as a designer, as someone who's designing the first passive house, what's the rule of thumb that I can go by to decide whether a HRV or ERV is better for my project? I think that would be important to know. How can I decide that?
Like when in doubt, ERV.
Okay, good one.
So maybe like ARV is most of the times not a bad decision. It's not always needed, but most of the times you're not making the wrong decision. But we can use a rule of thumb that I think works relatively good. Needs to still be proven properly. In my opinion, I haven't heard so many people using it yet. So we can look at a summer condition of 24 degrees with 50% relative humidity. 24 degrees is the indoor temperature and 50% relative humidity is the moisture. There we are at 9.4 grams per kilogram. Yeah, like 9.4 grams of a kilogram of air is moisture in summer. So I'm geeking out, guys. Yeah. So if you're not able to follow right now, it's okay. Yeah. Like even if you have done the designer course and you're not able to follow this, it's okay. I'm going now really into mechanical engineering and understanding. And if you're a mechanical engineer and you're not understanding it, it might be still okay. I'm not saying that that you need to know exactly what I'm talking about, but it's a rule of thumb that makes it easier. Yes, summer condition, 24 degrees, 50% relative humidity. Then we're speaking about 9.4 grams of moisture. Winter condition, we would look at 21 degrees at 45% relative humidity. There we speak about 7 grams of moisture in the air. That's the absolute moisture. Yeah, there's relative humidity. It's the percentage of how much moisture can be in the air, and the absolute moisture is telling you how much moisture is actually in the air. So the relative humidity is a percentage that is changing with temperature. Yeah, and the absolute moisture content is grams. Yeah, so if you have, for example, that 7 grams of 7 grams of moisture absolute at 21 degrees and you heat it up to 24 degrees, it's still 7 grams per kilogram, but it's not any longer 45% relative humidity. It's actually now probably 30% relative humidity because of warmer air can hold more moisture, so that 7 grams of moisture is less percentage of that moisture that can be in there. So yeah, but a psychrometric chart would be helping you on this. Again, another word that is super crazy. But okay, let's go
It's a
back.
bit of a
We look.
brain teaser, Daniel.
It's really
Bit
a
of a
brain
brain
teaser.
teaser you're putting in here. But yeah, really, really important. Once you understand it, makes so much sense.
So we're doing two edge cases: winter, summer edge case. Summer edge case at 24, 50%. Winter edge case 21 at 45% relative humidity. That's the edge cases. And then we look at our targeted moisture. What's our targeted moisture above? So say we have our summer edge case with our 9.4 grams. If we say it has now 9, 10, 11.4 grams of moisture that is coming in, then we definitely need to go for the ERV. And if it's minus 2 grams, so 5 grams per kilogram, then we would need to go for an ERV. So this is the edge case. Read the article, it's in there a little bit more in detail, but this is what you can say: 2 grams above or 2 grams below this edge cases. If you're in that range during the year, then it makes sense to go for an ERV. Yeah, but it happens relatively often, that edge case. Yeah, so it's more the normal than the unnormal. If you go for an HRV system, and then you realize, wait a second, in the summer the air is getting too sticky and too moist, or in the winter you're realizing it's getting too dry. Normally all the quality units can exchange the heat exchanger, and you can just replace it with an ERV. So you can then invest $500, and now you have an ERV and a HRV, and now you can actually jump between them. Yeah, you could now say, hey, in the extreme weather, so winter and summer, I'm using the ERV, and in between, I'm using the HRV. Yeah, it's the same unit. Yeah, it's just a different coil that we're putting in there. Okay,
Yeah.
that was spooky.
Oh, wow. Yeah. Maybe we should dial it down now after this exchange and a little bit of a brain twist. I think we've got a really nice example, a real life example that shows how we can use HRV in a different way. So maybe you want to, because it's one of your friends or acquaintances that
Yeah.
experienced that. So I think it's a
So
nice story.
is one of our former students, and yeah, I know him now a little bit. So what happened with them? They built a Passivhaus extension to a house. So the front house was still old, and the extension was built to Passivhaus, and then between the old part and the new part, they put in a door. So it was really like a separate unit in a way. And in there was one bedroom, a kitchen, dining, living area, and a bathroom, and a little study nook was in there. And that's where the parents were supposed to live. Yeah. And the kids live in the old place. Yeah. Like, don't know how much they love their kids. Okay, that's now mean. But they actually love them a lot, because what happened, the kids said, no, we don't want to live in the old part. We want to live in the new part. And what actually happened is the 3 kids moved now into the bedroom together. They prefer to live together. The kids, lived together now in the bedroom, and the parents lived in the study nook and had the mattress lying there, because everybody wanted to live in the new part. But now you have, instead of 2 people living there, you have 5 people living there. Instead of 2 showers, you have 5 showers a day. And now this was overloading the system, so that the CLT timber started to get a little bit of mold problems in places, because the moisture content went too high. The way that we were able to solve that was actually by just increasing the ventilation rate. Yeah, so
Mhm.
you just ramp up the ventilation volume, and by that we were actually getting out, because we had a higher use case. So sometimes you don't need to change, maybe you just need to ramp up your ventilation unit. Similar situation we had in a classroom setting, where we had a classroom with 35 students, that the moisture content went too high, and then I said we need dehumidification. And all we did, we went over the requirement, the normal requirement of Passivhaus for ventilation. And by this, we got the moisture content down and didn't need to change anything. So we didn't need additional technology like dehumidification to actually solve it. Yeah, so play around with the airflow rates as well if you're running into that problem. Sometimes by just ramping it up. If the outdoor condition is in favor, then ramping it up, it helps. If the outdoor condition is not in favor, maybe you have to reduce it, and that might solve it. Yeah. So, but this is not super geeky. Yeah. But still, we want to geek out sometimes.
Yes.
Yeah.
Perfect. But I think it already shows that there are options there, and looking into that really makes sense. Which system to use for your situation? You have to look at your project and see what's right for your project.
Yeah.
Cool.
And
Yeah.
one thing as well, what it really shows is spending money on somebody that knows what they're doing will save you money at the end because
Yeah.
you not have to do it twice or three times. Yeah. So you having somebody that understands it, that is done the training, that is experienced with this as well certification process, like having a certifier that is doing that for living for a long time. It totally makes sense to have them on board, even if you think you don't need certification. But these problems can be solved, especially with a certifier that is more experienced. Yeah. Yeah.
Cool. Very good. Do we want to clarify a few things that might be still confusing? For example, that ERVs don't dehumidify.
Mhm.
That's probably something that could be confusing.
Yeah. So because an ERV is separating moisture and temperature from the inside and the outside, the moisture stays inside, so it's not dehumidifying. So a HRV is in a way dehumidifying because it moves the moisture out of the building, but an ERV is not dehumidifying because it keeps the moisture in.
Yeah.
So, and this is something we want. If you have a lot of moisture outside, we don't want to get that moisture in. And if you have no moisture outside because it's super cold, then we don't want to get rid of all the moisture because then it gets too dry. Yeah,
Yes.
and that's not good for our expensive art pieces hanging around, like our Picassos. Yeah, and not good for our floorboards, and not good for our skin, and as well electric shocks, like these statics. They're happening more
Yes.
often. Dust buildup, I believe, is higher as well when that is
Mm.
happening. So yeah, so you want to have the relative humidity at the right level. Yeah.
And what about pools and other sort of wet
Mhm.
spaces that are not in our normal residential building? Is there something to look after?
Yeah, like indoor pools is always difficult. There is a whole standard with Passivhaus how to do
Mhm.
pools. So I think it's 200 something pages. There's one mistake in
Wow.
there, but it's so obvious you should find it. There, they explain how to do it and how to optimize it. Simplified said, you want to have in a pool to 99% of the times really a heat recovery, not an energy recovery, because you want to
Mhm.
get rid of that moisture. Yeah, you don't want to have that moisture
Yes.
building up, and as well, you want to keep the temperature in there as much as possible. So the heat recovery makes a lot of sense. You need to as well consider your location of your air tightness membrane. Intelligent air tightness membrane makes sense or not, because if you have such a high humidity in there, it might actually open up already before it actually needs to open up. So maybe the
Mhm.
intelligent membranes make no sense in there any longer. You may want to consider surfaces that are mineral based and flat. Yeah, so that you don't have mold growth on them. So better to have like tiles on it. That's the reason why bathrooms are tiled. That's the reason why
Yeah.
swimming pools are tiled. That's like, I'm not saying the magic stuff. It's just common sense. That is not so common. Anything else to consider? Anything what I forgot, Julia? Anything to mention there?
No, I think that's all. I think it's just really, I mean, this is not an everyday thing that happens, but if
Mm.
you're considering pools or some bigger wet areas, look into the standard. Really important to get yourself familiar with that. Obviously, it's a little bit of a um, different
Yeah,
situation.
yeah.
Cool.
As well, like even if you've done the designer course and this was now a little bit much for you, I totally understand it. We're going deep in here, but what is happening with doing this designer course or tradie course or so? You're coming to a point where you know you don't know. Before you didn't even
Yes.
know that you don't know. Like before you were like, oh yeah, everything is fine, but you don't see the thermal bridges, you don't see these things. Now you're getting more sensible, and now you say, wait a second, alarm clocks. Julia said or Daniel said, there is something to look out, and then you can actually solve it before it actually happens because you're aware that you don't know it, or you say, hey, there was something, let me check that again. Yeah, so it brings you to this next level of understanding. I'm at that level where I'm consciously I unconsciously know, like it for me it's a physical understanding. Like I just
Yes.
feel it. It's right or it's wrong. And that's when you're really living and breathing it and doing it the whole time. Yeah, it's a passive house sense. Yeah, yeah. It's
Yes.
like smell, like you smell it, like something is off. Yeah, that's not right. Cool.
I think that's a really good point. If you're not sure, ask the experts. Ask the people that are in the field that do have the knowledge. I think that's a really, really important thing. You don't have to know everything, but you have to know who to ask. So
Yes.
that, as Daniel said, if there's something you didn't understand in this, ask someone, and that's already a big step further than most people are in
Yeah.
this.
Because you know that you have to ask. Yeah.
Exactly.
And there's a huge community out there.
So yeah. Now you know the difference between HRV and ERV and which one you should use in your situation. Also, this was a little bit geeky and a little bit into depth with how this all works. So if you know someone who likes these kind of things, share the article with them, like us, subscribe, press the button. It helps to get it in front of more people, all this knowledge that is so important to know. And I will see you, or we will see you next week for our next Passive House Weekly. There we will talk about what it means to become a certified Passive House tradesperson and how important it is that we have enough certified tradespeople around. Okay, I'll see you then. Bye.